You probably already know that nanotechnology deals with things that are, incredibly small.
Right.
But let's put that scale into perspective for a second.
Ah.
Imagine trying to build a perfectly functioning, life-size replica of the Eiffel Tower.
Okay.
But your only building materials are individual grains of sand, and you have to place them one by one using a pair of tweezers.
Oh, wow. Yeah, I mean, that is a staggering engineering challenge.
Right.
You are essentially trying to construct this massive architecture where every single foundational unit has to be perfectly aligned
Yeah.
because otherwise the entire structure behaves unpredictably.
Exactly. And that microscopic, painstaking precision is the reality of what we are unpacking today. So welcome to the deep dive.
Glad to be here.
Our mission today is to shortcut your way to being completely well-informed about a field that is, honestly, actively rewriting the rules of our physical reality.
It really is.
We are looking at a comprehensive breakdown from support tips technology, and it explores the manipulation of matter at the nanoscale. So, okay, let's unpack this.
Let's do it.
We are the builders with the tweezers, and the atoms are the grains of sand. But what I found so compelling in this data is that we aren't just shrinking existing technology down. We are dealing with an entirely different set of physical laws.
Yes. That is the crucial paradigm shift here. When you shrink matter down to the nanoscale,
Which is what
it's
exactly?
roughly 1 to 100 nanometers.
Okay, got it.
Yeah. So at that scale, the normal rules of classical physics, they just begin to give way to quantum mechanics.
Which is wild.
Right. At that scale, a material's surface area to volume ratio just explodes. You expose so many more atoms to the outside environment that the material suddenly exhibits completely unique mechanical, electrical, and chemical behaviors.
So it actually acts differently.
Exactly. Take gold, for instance.
Yeah.
It isn't even gold-colored at that scale. It can appear red or purple.
Wait, really? Red gold?
Yeah. You aren't just making a material smaller. You are fundamentally altering its identity.
Which means a single element can be engineered to do things it could literally never do in nature.
Precisely.
To understand the sheer scale of this invisible revolution, we have to look at how it's currently hiding in plain sight.
It's everywhere.
Right. Let's start with the immediate environment around you, like the gadgets we use every single day. The data points out that in electronics, nanotechnology is the reason our devices keep shrinking while getting, exponentially more powerful.
Yeah, because we've largely hit the physical limit of how small we can cut traditional silicon.
Exactly. So the industry has pivoted to entirely new nanoscale materials, like carbon nanotubes and graphene.
And graphene is a perfect illustration of this quantum shift. It is a single layer of carbon atoms arranged in a two-dimensional hexagonal lattice.
So, like atomic chicken wire?
That's a great way to put it, yeah, atomic chicken wire. Because it is only one atom thick, electrons can zip through it with almost zero resistance.
Wow.
By integrating graphene and carbon nanotubes, engineers are creating high-performance transistors and memory devices that run faster, generate way less heat, and consume far less energy than anything silicon could achieve on its own.
So that's how we get these hyper-powerful gadgets that fit in our pockets without, melting in our hands.
Exactly.
But the applications go way beyond microchips. I mean, we are talking about consumer goods and manipulating materials to create self-cleaning surfaces or highly scratch-resistant coatings for your eyeglasses.
Right.
But wait, how does a surface actually clean itself at the atomic level?
Well, it often mimics something called the lotus effect found in nature.
The lotus effect.
Yeah, by engineering microscopic bumps on a surface, like a glass lens or a building material, you reduce the contact area for water droplets.
Okay.
So the water can't adhere to the surface, it just beads up and rolls off. And as it does, it collects and carries away dirt particles.
Oh, that makes sense.
What's fascinating here is that we are engineering the physical environment to naturally resist degradation. We are taking basic construction materials and making them exponentially stronger just by tweaking their molecular geometry.
That's incredible. And we've mastered wrapping our buildings and screens in these materials, but we're also wrapping our bodies in them.
Oh, definitely.
The breakdown on textiles completely changed how I look at my closet, honestly. Nanoscale coatings are applied to fabrics to give them that same water repellency, along with stain resistance and UV protection.
And it gets even more complex with smart fabrics.
Right. By integrating nanomaterials directly into the woven threads, clothing can actively regulate temperature, manage moisture, and deploy antimicrobial properties.
It turns a passive object into an active functional tool.
Yeah.
The fabric itself is working to maintain a specific microclimate against your skin. And that lays the groundwork for continuous healthcare monitoring directly through the clothes you wear.
Which naturally brings us to the actual barrier of the skin. The cosmetics and personal care industry is heavily invested in this space.
Huge investments, yes.
The research highlights how nanoscale ingredients, specifically nanoparticles and liposomes, are used in skincare.
Right.
Because they are so unbelievably small, they can breach the skin barrier effectively. They act as tiny delivery vehicles, bringing active compounds exactly to targeted areas.
Or creating sunscreens with vastly superior UV protection because the particles distribute so perfectly.
Exactly. But reading through this, I have to raise a question.
Sure.
So if we are basically rubbing nanomaterials into our skin with our lotions and wearing them on our smart fabrics, wait, no, let me rephrase that. What is the actual difference between a nanomaterial and a nano device? Are my stain-resistant pants just chemical structures, or are they tiny machines?
Yeah, that's a really good distinction to make. It comes down to computation and moving parts.
Okay.
When we talk about a nanomaterial like the scratch-resistant coating on your glasses, the lotus effect bumps, or the liposomes in your moisturizer, we're talking about passive structures.
Passive. Got it.
Right, we have manipulated the atoms so that the material naturally repels water or safely encapsulates a vitamin based purely on its chemical and geometric properties.
It doesn't have a power source.
Exactly. It isn't calculating anything.
So it's just a highly optimized static substance.
Precisely. A nano device, on the other hand, involves active manipulation.
Like what?
It combines electrical and mechanical properties at that microscopic scale to perform a specific function, like a sensor reacting to a change in temperature or a transistor switching a current on and off.
I see.
Your stain-resistant pants aren't mechanical machines. They are perfectly engineered chemistry.
That makes a lot of sense. So we've seen how this perfectly engineered chemistry is applied to our external environment.
Yeah.
But the data takes a fascinating turn when we look at what happens when we put this technology inside our biological systems and our environment.
It really does.
Let's move into food, agriculture, and medicine.
This is where the implications scale up from daily convenience to vital human survival.
Right. In food and agriculture, the sources detail how nanoscale additives and encapsulation techniques enhance both the nutritional value and the shelf life of food. But out in the fields, nanotechnology is allowing for the precise, controlled release of fertilizers and pesticides. I was looking at how much traditional agricultural runoff damages river ecosystems, and it seems like this nanoscale encapsulation acts like a time-release pill for the soil.
That is the exact mechanism.
Right.
Yes. Instead of dumping raw nitrogen onto a field where, 80% of it washes away in the next rain, you encapsulate the nutrient in a nanoscale polymer shell.
Oh, wow.
And that shell is engineered to break down only under specific triggers,
Like what kind of triggers?
like a certain soil moisture level or the specific pH of a plant's root system. The chemical is released slowly and only exactly where the plant needs it.
That's brilliant.
It is. You drastically reduce the environmental footprint while actively boosting crop yields. Furthermore, nanosensors are deployed to detect contaminants and pathogens in the food supply, ensuring safety long before an outbreak occurs.
That concept of hyper-targeted precision extends directly into human healthcare, too.
Absolutely.
And here's where it gets really interesting. Think about traditional medicine. A systemic treatment like chemotherapy is essentially a carpet bombing approach.
Unfortunate, but true.
Right. The drug floods the entire system, and the whole body suffers brutal side effects in the process of trying to eradicate the disease.
It is an effective but highly collateral strategy.
Yeah.
The medicine just cannot distinguish between a healthy cell and a cancerous one.
But nanomedicine changes the entire paradigm.
It does.
The research explains that nanoparticles can be engineered for targeted drug delivery. It's like deploying a highly trained molecular sniper. But how does that actually work? How does a nanoparticle circulating in the bloodstream know to only attack the cancer cell?
It comes down to something called surface functionalization.
Surface functionalization, okay.
Yeah, so scientists can attach specific molecules like antibodies or protein ligands to the outside of the nanoparticle carrying the drug.
Like a tag.
More like a highly specific physical key. Cancer cells often express unique receptors on their surface that healthy cells do not have. I see where this is going.
Right, so the nanoparticle circulates harmlessly through the body until its key encounters the exact matching lock on the surface of the tumor cell.
Wow.
It binds to it, enters the cell, and releases the toxic payload directly inside, leaving the surrounding healthy tissue completely untouched.
That is a profound shift, moving from reactive broad-spectrum treatment to personalized precision medicine.
It really is.
And that extreme sensitivity applies to diagnostics too, right?
No, absolutely.
The data notes we can detect diseases at their absolute earliest stages. The nanosensors are looking for the very first molecular whispers of the disease, like a single biomarker protein, long before a traditional MRI would pick up a visible tumor.
And perhaps even more revolutionary is what happens after the disease is treated or an injury occurs.
What do you mean?
The source highlights how nanomaterials are utilized to engineer tissue scaffolds and implants for regenerative medicine.
Giving the body an architectural blueprint to rebuild itself. Yes. When tissue is severely damaged, the body sometimes struggles to bridge the gap with healthy cells, resulting in scar tissue.
Right.
By inserting a nanoscale scaffold that mimics the natural extracellular matrix, we provide a physical structure for the patient's own cells to grip onto and grow around.
That's incredible.
We are no longer just treating symptoms. We are giving the biological system the exact tools it needs to repair itself perfectly. It is a true paradigm shift for human longevity.
So we are fixing the human body and securing our food supply with invisible tools.
Yes.
But human survival also depends on solving massive, macro-level planetary crises, which raises the question, can the microscopically small actually fix the globally massive?
Well, when it comes to the macro crises of energy and water, the evidence suggests this is one of our most viable paths forward.
Let's look at energy. The data explains how harnessing nanomaterials is leading to vastly more efficient solar panels.
Right, by using elements like quantum dots.
Quantum dots, those are nanoscale semiconductor particles, right?
Exactly. And with them, we can manipulate how the material interacts with light. They can be tuned to absorb different parts of the solar spectrum that traditional silicon panels completely miss.
Oh, so they catch the light that usually goes to waste.
Precisely, resulting in a much higher efficiency in converting sunlight into electricity.
And once we have that power, nanotechnology is revolutionizing how we store it too, with nano batteries and supercapacitors.
Which is huge because energy storage is the critical bottleneck for renewable energy.
Yeah, the sun doesn't always shine.
Right. If we cannot store solar and wind power efficiently for when the sun sets or the wind dies, the grid cannot transition away from fossil fuels.
Makes sense.
By using nanomaterials in battery electrodes, we vastly increase the surface area for electrical charge transfer. This means nano batteries offer faster charging, longer lifespans, and significantly greater capacity.
And then there is water.
Yes, water.
The source highlights nanofilters and membranes that offer cost-effective and sustainable solutions for desalination and water purification. These filters are so incredibly precise they can remove pathogens and chemical contaminants at the molecular level.
They are very effective.
But I need to pause here because I caught a glaring paradox in the research.
What stood out to you?
Well, the breakdown specifically mentions that these highly efficient filters are capable of removing contaminants, pathogens, and even nanoparticles from water. So we are using nanotechnology to clean up nanotechnology.
It does sound a bit cyclical.
Right. As we put nanoparticles in cosmetics, fertilizers, and clothing, they inevitably wash into the water supply. It feels like we are creating a new type of microscopic pollution and then desperately inventing nanotech filters just to clean up our own mess. It feels like we're constantly chasing our own tail.
It is a valid concern, and it really highlights a fundamental reality of rapid innovation. If we connect this to the bigger picture, technology very often has to evolve to manage the secondary complexities it introduces into the environment.
But isn't there a risk that we are outpacing our ability to clean it up?
There is always a risk when introducing novel materials into an ecosystem. The fact that nanofiltration can capture these runaway particles is crucial for environmental management.
True.
However, we have to weigh that cyclical paradox against the immediate macro-level benefit. For regions facing severe water scarcity, reverse osmosis plants using nanomembranes are the difference between a thriving city and complete collapse.
That's a good point.
These membranes can desalinate ocean water with far less energy than older methods, and they can purify heavily polluted sources to a pristine state. They are addressing one of the most critical global challenges we face today.
So the tool is essential for survival, even if it has to simultaneously manage the side effects created by its own existence. I think that is the reality of any major industrial shift. And having addressed those foundational human needs, health, food, water, and energy, The source material takes us into what I can only call the wild frontier.
The fun stuff.
Yeah. This is where nanotechnology pushes the absolute boundaries of our physical reality, entering the realm of science fiction.
This is where we move from improving existing systems to fundamentally redefining what is physically possible.
First up, the research introduces us to NEMS, nanoelectromechanical systems.
Right.
These are the active nano devices we discussed earlier, where electrical and mechanical properties are combined. We are talking about highly sensitive sensors and actuators.
Like the ones in our phones.
Exactly. The tiny accelerometer in the smartphone you might be holding right now, the component that knows when you turn your phone sideways to watch a video, is a NAMS device.
Yep.
Inside that chip is a microscopic physical silicon diving board that actually bends when you move the phone, and that physical movement is translated into an electrical signal.
It is the invisible bridge between the digital processing world and the physical kinetic world.
But the section that truly blew my mind is optics and photonics, the science of light manipulation.
Oh, this is fascinating.
By engineering materials at the nanoscale, researchers are developing photonic crystals and plasmonic structures that give us unprecedented control over how light propagates.
Right.
But then the data introduces metamaterials, and it explicitly states that metamaterials possess a negative refractive index, offering the possibility of invisibility cloaking.
Yes, invisibility cloaking.
I want to make sure everyone listening grasps the mechanics of this. This isn't a camera projecting a background image onto a screen. This is actual invisibility. So what does this all mean? How does a negative refractive index work?
Well, when light hits normal matter, it bends or refracts inward.
Okay.
Think of how a straw looks broken or bent when you place it in a glass of water. That is a positive refractive index.
Right, I can picture that.
But metamaterials are engineered at the atomic level with structures smaller than the wavelength of light itself.
Whoa.
These structures force the incoming light waves to bend backward, effectively routing the light waves entirely around the object, much like water flowing smoothly around a boulder in a stream and reconnecting on the other side.
That is insane.
If the light doesn't bounce off the object and hit your eye, the object is completely invisible to you.
We are literally hacking the physics of light.
We are. And this raises an important question, and it requires us to completely reevaluate our understanding of limits.
How so?
If we can manipulate light so perfectly that an object becomes invisible, we are proving that the physical constraints we thought were absolute are actually just engineering challenges.
Wow.
You see that same philosophy applied to space exploration in the research.
Yeah, the data mentions that nanotechnology is providing lightweight, ultra-durable materials for spacecraft. When every ounce of weight costs thousands of dollars to launch into orbit, synthesizing a material that is incredibly light but stronger than steel alters the economics of space travel entirely. Plus, nanoscale sensors are being developed to study the cosmos, alongside revolutionary new propulsion systems.
But the true frontier, the concept that pulls all of these separate disciplines together, is nanorobotics, the convergence of nanotechnology and automation.
The nanobots.
Yes, nanobots.
Yeah.
We already touched on how passive nanoparticles act as molecular snipers in medicine, but true nanorobotics implies active, programmable machines performing complex tasks.
Like little robots swimming around.
Exactly. The source points out that these could perform highly precise cellular surgery. But the most disruptive application mentioned is in manufacturing.
Manufacturing.
Yes. Nanorobots could enable the fabrication of intricate macro-scale structures with unmatched atom-by-atom precision.
So, returning to our original visualization, building the life-sized Eiffel Tower out of individual grains of sand, but it's being built by billions of automated, invisible tweezers.
Exactly. And that capability, molecular manufacturing, could entirely upend how everything on Earth is built.
Yeah.
From the smartphone in your pocket to the spacecraft heading to Mars.
Just building it atom by atom.
Right. If you control the atomic structure of a build from the ground up, you control the final product with zero waste, perfect efficiency, and total structural integrity.
It is absolutely staggering to think about. We set out on this deep dive to shortcut our way to understanding nanotechnology, and the sheer breadth of what we've covered is astonishing.
It really is a massive field.
From the passive liposomes in the sunscreen you might have put on this morning to the NMS accelerometer tracking your steps. From the targeted molecular snipers of modern cancer treatments to reverse osmosis water filters and the literal bending of light to create invisibility cloaks.
Yeah.
Nanotechnology is the invisible thread connecting the present to the future of humanity.
It is, and it leaves us with a profound concept to consider.
What's that?
Well, we talked about nanorobotics and the idea of molecular manufacturing, building things atom by atom.
Right.
If you follow that logic to its ultimate conclusion, it fundamentally challenges how we organize our civilization.
In what way?
If nanobots eventually allow us to build any material from scratch,
Hmm.
if we can theoretically rearrange cheap, abundant carbon atoms into perfect diamonds, or synthesize rare earth metals out of basic organic matter, what happens to the global economy?
Oh, wow.
When we can manipulate matter so perfectly that the concept of scarcity no longer exists, does the value of physical things drop to zero?
That is a massive paradigm shift to chew on. It makes you realize that those invisible grains of sand being placed by those microscopic tweezers aren't just building new gadgets.
Oh, they aren't.
They might be building an entirely new economic reality.
Indeed.
We want to thank you for joining us on this deep dive into the invisible world. The next time you put on a pair of scratch-resistant glasses or marvel at how small a new device is, we encourage you to look a little closer at the materials around you.
It's all right there.
The future is already here. It's just really, really small.
Consumer, you